Video 25 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is pseudo-perturbation theory. In the lecture on the time-dependent response theory, we could see that the polarization propagator or linear response function has poles at the excitation energies of the system, meaning at the difference between the energy of an excited state of the system and the energy of the ground state of the system. One can see that by looking at the spectral representation or sum over states expression for the linear response function in the frequency domain. Now, in the last chapter, we derived a matrix representation for the polarization propagator or linear response function, which was the product of the property gradient vectors and the inverse of what is called the principal propagator. Now, from this matrix representation, we can then conclude the response function or polarization propagator will have a pole, meaning a singularity, when the principal propagator matrix becomes singular. Now, singularity of a matrix, that's also a condition for solving a set of homogeneous linear equations, which means looking for which values of the frequency omega the principal propagator becomes singular, meaning the response function has a pole, corresponds or is equals to looking for the solutions of this set of homogeneous linear equations, looking for the values of the frequency omega for which this set of equations has a solution. Now, this set of homogeneous linear equations has a particular form because the matrix here has two contributions, which means I can rewrite that by moving half of it to the right hand side. I can rewrite it to this equation, which we can recognize as a different kind of mathematical equation, because this is just an eigenvalue problem, or to be more precise, it's a generalized eigenvalue problem because we have this overlap matrix here, which in the context of the eigenvalue problem takes over the role as a metric. So we have our matrix E here. Omega are then the eigenvalues, and R here is the eigenvectors, and because it's the eigenvector standing to the right of the matrix, we call this the right eigenvector. And we know now, because of the argument which I just came with, that these eigenvalues here, the eigenvalues are the values of the frequency omega for which this homogeneous set of linear equation has a solution, which means for which this matrix becomes singular, and that means these are exactly the excitation energies of our system. Now, if the Hessian matrix is asymmetric, then the right and the left eigenvector are not the same. So we can also write up an eigenvalue problem where we have a left eigenvector. It has the same eigenvalues because they are the same, but these eigenvectors L are different than the right eigenvectors are if the matrix E is asymmetric. Now, having a generalized eigenvalue problem here with the metric S, which is our overlap matrix from the linear response function, one then normally orthonormalizes the eigenvectors over the overlap matrix S in this way here. So I have a left eigenvector and a right eigenvector, and carry out this matrix multiplication. And I require that the vectors are, this product gives a Kronecker delta, meaning they are orthonormalized over the overlap matrix. For a symmetric Hessian matrix, the left and the right eigenvectors are the same, but one still uses this orthonormalization condition. Now, in this lecture, we want to look at a situation where we have our generalized eigenvalue problem, but for some reason or another, we do not wish to solve this generalized eigenvalue problem itself. Probably because it's too time consuming, too expensive, too difficult to solve. But we can define an eigenvalue problem which is an approximation to the original one. And that one we want to solve. So we want to solve this here approximate eigenvalue problem where we have approximated the matrix E and the overlap matrix S, and then have an eigenvalue problem for the right eigenvectors and an eigenvalue problem for the left eigenvectors. So we assume that we have solved these equations, and starting from these equations, we will now use perturbation theory to get approximations to the eigenvalues and eigenvectors of the full problem. And we do that in the way that we take the Hessian matrix and the overlap matrix of the full problem, and we partition them in a series of matrices, where the first one is these approximate matrices E0 and S0, the one for which we can or want to solve the eigenvalue problem, and we have solved the eigenvalue problem. And then we can define, and that we are free to do as it suits us, we can define then correction to this zeroth order matrix here, which when adding all the corrections together, we will get the original matrix then. And in principle, there can be many corrections in the examples which we will later on look at in later chapters of the book. We probably already get the full matrix by having a first order and a second order correction already. But in general, there could be more terms. So we start with this partitioning of our original Hessian matrix and overlap matrix. And then we will derive also, and we have solved the zeroth order matrix. So we know the zeroth order eigenvalues, and we know the zeroth order right and left eigenvectors. And then we're going to derive corrections to the zeroth order term, first order term, second order term, and so forth, and assume that this is a converging series so that we eventually approximate the eigenvalue of the full generalized eigenvalue problem and the eigenvectors of this by this perturbation series expansion. Now one can, of course, do this partitioning here of the matrices as it pleases one, or as it is appropriate for the makes sense in the context of what kind of matrices one is dealing with. But it's actually an advantage to choose the first order correction to the E matrix and the S matrix in such a way that their contribution to first order is 0. So if I multiply the first order E and S matrix by the right with the zeroth order eigenvectors and by left with the from the right with the right eigenvectors, from the left with the left eigenvectors, that this gives 0. As a consequence of this, the first order correction to the eigenvalues later on will be also 0. Now we can insert the expansion of our E and S matrices and of the eigenvectors in our original generalized eigenvalue problem. But this equation, which I haven't written up here, I can then separate like normally in perturbation theory in the zeroth order equation, which we already sort of know, and then in a first order equation containing terms only to first order, and in a second order equation, and so forth. Now in the first order equation, of course, we have the first order correction to the E matrix times the zeroth order right eigenvector, which gives us a first order term, and the vice versa with the zeroth order E matrix and the first order correction, and similar on the right hand side. And the same we will have here for the second order equation, where I have here the second order correction to the Hessian with the zeroth order right eigenvector, product of two first order corrections, and the zeroth order E matrix multiplied with the second order correction to the right eigenvector. Now in order to get expressions for the different corrections to different orders to the eigenvalue, we do precisely the same as we do in the normal perturbation theory. So we project from the left with the zeroth order eigenvector now, and here it has to be, of course, then the left eigenvector. And if we do that with the first order equation and also with the second order equation, things we have used the normalization of the zeroth order eigenvectors, which is over the overlap matrix, which means that if I multiply from the left here with the zeroth order left eigenvector, then this term here, where I have the right eigenvector standing on the right, is essentially just a normalization of the two eigenvectors. So this gives me just omega n first order. And if I multiply here on the left-hand side with the 0th order left eigenvector, I can make use of this requirement, which I said before, which means this term is also 0. Is these conditions, which means we obtain those equations here, where we already have used now, which means at the end I arrive at this expression, where I have the first order correction to the eigenvalue as being this product. But this product is just, again, as I said already, 0. Now the second order equation, at the end I arrive this expression here. And if you look at that, you can see that this very much looks like an expression we had in normal perturbation theory. Because what do I have here? I have the 0th order left eigenvector and the 0th order right eigenvector. And here the second order corrections to the overlap matrix and to our Hessian. That corresponds in normal perturbation theory. That would be the expectation value, the ground state expectation value, because that's the two 0th order wave functions of the second order correction to the Hamiltonian. Here we have the second order correction to our matrices, because what is the Hamiltonian in normal perturbation theory? Here it's our matrices in the pseudo perturbation theory. And correspondingly, this term here, what do I have? I have the 0th order left eigenvector. Then I have first order corrections to the matrices. And then on the right side, I have the first order correction to the right eigenvector. So this is the term which becomes the sum over states term in the second order energy correction, which is a matrix element of the 0th order wave function, first order Hamiltonian, and the first order wave function. Besides like this. Now I can rearrange. So in order to sort of finish, I need to find out what this first order correction to the right eigenvector is. And I can get this by rearranging my first order equation. So I can isolate the first order correction to the right eigenvector from my first order equation before. And I get this expression here, which also very much looks like the first order correction to the wave function, because I have a denominator which is a 0th order energy, and here is my 0th order corrections, 0th order term in the my matrix. And in the numerator, I have a first order term and a 0th order eigenvector, 0th order right eigenvector here. Now if I insert this in here, the first term is still the same, and the second term becomes now a bit more complicated, where I have now my 0th order left eigenvector. I have this first order correction to the matrices. Then I have my 0th order matrices, and taking the inverse, multiplied again with the first order correction to the matrices, and then the 0th order vector. So this is very much the same structure as the sum of states expression. Now what did we gain? We started out having an expression where we would have to solve an eigenvalue problem with a full matrix. Now we end up with having to solve only the 0th order equation. And then we have a correction here, two corrections, but in both of these corrections, here we have the second order matrices, but this is just a matrix multiplication, so there's no inverse. The only place where we have to calculate an inverse is actually here again of the 0th order matrices. So one chooses the 0th order matrix in such a way that the calculation of this inverse here is not difficult to do. And then it's easy to calculate the second order correction. We will later on in the third part of the book discuss two methods where this is used in order to get an approximation to a more complicated method, a cheaper approximation to a more complicated method.